Okay, so the next talk is on public signals and network congestion games, and it's by Svenja.
Yeah. Hi, and welcome to this talk. So, yeah, this is some joint work with Martin Hoefer, with my advisor Max Klimm, and with Tim Koglin, who's also sitting in the audience. So, yeah, let's start right with our model. So, in our model, we are looking at a directed ST graph. And now we have a commodity of size 1, which wants to travel from S to T. However, now on each edge, we have a cost function. And in our case, this cost function is an affine cost function. So this x basically tells us how large is the population that uses this edge. And then we have an additional offset b. And as we can already see on this formula, is that this b depends on some state theta. And for this example today, I want to look at the set with just two states. And one is the good weather situation, and one is the bad weather situation. So this graph up here, for example, could be the cost functions for the good weather situation. And then for bad weather, we have the same graph with a similar cost function, but the offset is different. So now what do? We as a participant, of course, want to choose the fastest way to get from S to T. But obviously now this depends on in which state we really are. However, we as a participant, we never really know which state is actually realized. All we know is a given prior distribution mu. And this is basically just a probability distribution over the set of states. So we know, for example, okay, with probability of 40%, we have the bad weather situation, and with a probability of 60%, we have a sunny day. So what do? Well, suppose we knew that it was a sunny day. Then we know for sure, okay, we are in this upper graph. And then everybody would take the lower edge because that's the fastest way to get from S to T. And since we have a population of size 1, we end up with a cost of 2. In the other case, so let's suppose now that we know that it's a rainy day or a cloudy day, then we know for sure we are in the lower graph. And then the fastest way to get from S to T is the upper edge. And we will end up with the same cost of 2. However, as I already said at the beginning, we usually don't really know the state. All we know is this given prior. So we know, okay, with probability of 40%, we're in the lower case. And with a probability of 60%, we are in the upper graph. So what do? Well, we kind of combine those two graphs. And then have this new cost function, which depends on this given prior. And now in this graph, we try to find the fastest path from S to T. And in this case, the commodity will split up between the medium path and the lowest path. And we will end up with a cost of 3. OK, so let's put this into another graph. So here on the x-axis, I'm looking at the probability of the bad weather situation. And on the y-axis, I'm looking at the cost that occurs in equilibrium. And with equilibrium, I mean that everybody, I'm talking about water-up equilibrium, so nobody has an incentive to deviate from their chosen paths, because all chosen paths have the same cost, and every path which is not chosen by anybody costs at least the same and maybe even more. So we've already seen, if we knew that it was sunny, so probability of rain would be 0, then we would end up with a cost of 2. And if we knew it was raining, we would end up with a cost of 2 as well, so that's the blue point. And if we just act upon our prior, we have the cost of 3. And we can, of course, compute this cost for any given prior, and then we end up with this cost function here. And note that this is, in this case, piecewise linear and concave. And why this is important, we will see it a little bit further to the end of this talk. OK, but however, what we are doing actually is information design. So why is it called information design? Because there's somebody in our model who has an information advantage. And in this case, this is a traffic service provider. So if we're not, for example, looking at sunny weather and bad weather, but rush hour or a traffic jam or anything, then we could imagine this traffic service provider is Google Maps or TomTom, and they have all the data. They know for sure which state is actually realized. So now the question is, what do they do with their information? And one thing is they could just keep the information for themselves. They see what state is realized, but they just don't tell us. So what do we do in this case? Well, all the information we have is this given prior mu, and of course the cost functions depending on which state. But all we can do is just play according to our prior, and then we end up with a cost of 3. Another thing the traffic service provider could also do is just do full information revelation. So they see which state is realized, and they give us all information. And then what do we do in this case? Well, then we always know which state is actually realized, and we can either, we know if it's sunny or bad weather situation, and then in both cases we end up with a cost of 2, so also in total we will always end up with a cost of 2. Okay, so the question that naturally arises is, what information should the traffic service provider reveal now in order for us to have the lowest cost as possible in expectation? And how this works is actually that we say our traffic service provider, they commit to a signaling scheme. And what do I mean by signaling scheme? Well, the signaling scheme is something that we can kind of visualize as a bipartite graph. So on the one side, we have all the given states, which is in this case just sunny weather and bad weather, and their probabilities. And then there's also a set of all possible signals that this traffic service provider can give to us. So for this case, let's say they can either flash green light, blue light, or red light. And now the signaling scheme itself basically tells us what is the probability that we obtain signal sigma and state theta is observed. And in this graph, this is basically the edges. So as we can see here, when it's sunny weather, which happens with a probability of 60%, then the traffic service provider will flash green light with 10% probability, blue light with 20% probability, and red light with 30% probability. And in total, this, of course, has to add up to those 60% chance of good weather. And these signals are, as the name suggests, public signals. So everybody gets the same signal. And now what do we do with the signals? Well, since we as a participant, we know the signaling scheme. So we know the edges and their weights kind of. And now this signal that we obtain induces a new prior. So for example, we obtain a green light. Then we can see in this graph, okay, with 10% probability, this comes from the sunny weather situation. And with 30%, this comes from the bad weather situation. So if we combine this, then now we know, okay, well then the chances of a good weather day is 1/4, and the chances of bad weather is 3/4. And we can do this, of course, for all 3 different signals. And then in this cost function graph that we already saw in the beginning, we can now see, okay, with if we have a green light, then in equilibrium we will have a cost of 3, and so on. Okay, so this is one example of a signaling scheme. Next, I would like to give you a second example and then show you what an optimal signaling scheme would look like. So here I'm looking at this directed as T graph, and those are the costs for the sunny weather. And then for the bad weather day, we have those costs, and note that the only 2 edges which change their costs is this vertical one in the middle, which changes from 0 to 6, and the outside edge where the cost decreases from 3 to 0. So if we, for example, knew that it was sunny today, and of course the probabilities for each state. So if we now knew that it was sunny, then everybody would take the zigzag path, because that's the shortest way to get from S to T. And if it's a bad weather situation, then everybody will go use the outside edge, and we will have a cost of 0. And if we now compute this cost function graph for all kinds of given priors, then we actually have a cost function which looks like this here. So now we said that the prior that we are given, so the chances of rain are 1/3. And now we can see in this graph, well then in equilibrium we will have a cost of 3/2. So now the question is, can we decrease the cost? And here in this example, we can see it kind of nicely, because what we're actually looking for is the best convex decomposition of our given prior. And what we see is that if we would always end up in one of those two equilibria, then in expectation, we would decrease our cost for this equilibrium by a lot. So how do we end up in these situations? How would the signaling scheme look like in order for those costs to occur in expectation? Well, of course, we have to start with the one side of our bipartite graph where we have the two states. And then in order to distinguish between those two signals, we of course assign them just different colors, for example. So there's either the green light which is flashed or the red one. And now all that's left are the edges of our bipartite graph. And here in this case, whenever there's sunny weather, then the traffic service provider will always flash the green light. He will never flash the red light. But if it's a bad weather day, then the traffic service provider will randomize between green and red light with a probability of 2/33 for the green light and 9/33 for the red light. And now those are the priors which are then induced by this signaling scheme, and that's exactly what we want. So if the green light is flashed, then we know with probability of 1/12 we have a rainy day, and that's exactly what we want here in this graph. And if the red light is flashed, then we know for sure today is definitely a rainy day, so we're on the very right, and that's exactly what we wanted to obtain. Okay, so now before I go into our main results, let me give you a short review of some known results, and I just want to focus on two things. And one is that full information revelation is always a 4/3 approximation. This basically comes from the price of anarchy, and you can see this in Rough Garden and Tardos, for example. And the other result is by Bashka and others, and they focus on optimal signaling scheme for single commodity networks. And they actually show that it's NP hard to approximate those optimal signaling schemes by a factor of 4/3 minus epsilon. And for their hardness proof, they require E many different states. So just looking at this already seems kind of tight. So we know we cannot really get better than 4/3, but we can already obtain this 4/3 by just giving full information revelation. But there's two things that I would like to mention here. First thing is this holds for general graphs, but maybe there is a specific set of graphs for which full information revelation is even a little bit better. And the other thing is the requirement of E many states is a lot. I mean, if we just imagine we are in New York and we want to build one more road, then we would require an additional weather condition, for example, for this hardness to hold. So maybe in real life we don't need that many, there's not that many states. Okay, so let's see what the main result of our paper is. And it's stated as follows. So full information revelation is actually an optimal signaling scheme for all instances based on a single commodity network G, if and only if this graph is a series parallel graph. And if we remember the example from the very beginning, this is obviously a series parallel graph since we only have 3 parallel edges. And the cost function that we obtained was this one. And maybe you remember what I said, this is piecewise linear and concave. And this is super nice because now if we just take any convex combination of the 2 full information points at the very ends, then this basically shows us the costs in equilibrium, in expectation, and this is the lowest cost we can ever get. We cannot put this, this line even lower. And this is also how our proof kind of works. So the first things we show is that the cost function is piecewise linear, and the second thing we need to show is that it's also concave if and only if G is series parallel. Okay, so now we know whenever we have a series parallel graph, we just do full information revelation, and that's perfect. So what do we do if the graph is not series parallel, or maybe we have multiple commodities? And this is exactly the second part of our paper where we come to computing optimal signals. And let me just state the theorem real quick. So here we say that optimal signals can be computed by an LP of size polynomial in K, the number of vertices and the number of edges. So there's two questions arising. First, what is K? We'll get to this in a second. And the second thing is where we already know it's NP hard. So this K cannot be really just it must be something that may grow exponentially. So let's have a look at what this K really is. So this K actually is the number of supports that appear in our cost function in equilibrium. So what do I mean by this? Well, in this example from the beginning where we had the +5 for the sunny weather situation and the +4 offset just for bad weather, we had this cost function. And now if we knew that it was sunny, everybody takes the lower edge. So this is the first set of edges that is used in the equilibrium. But as soon as rain becomes more probable, we switch to different set of edges. So here's the second set of edges which is used, then a third one, a fourth one, and a fifth one. So for this example, we have 5 different supports that are used. So here the K would be 5. And as I already mentioned, this K may be exponential in the number of vertices and edges. But for realistic networks, this K is actually rather small. OK, so just a short summary. Well, at the beginning, we saw that optimal information design leads to the problem of finding a cost minimal convex decomposition of a given prior. But we also saw that if the graph is series parallel, then always full information revelation is optimal. Then we saw that we can actually compute optimal signals in time polynomial in K, where K was the number of supports, and this K may be exponential. But we also observed that this is rather small for realistic networks. Yeah. Thank you for your attention.
Yeah, thank you very much. Are there any questions?
So, do you know of any underlying graph structures where full information revelation becomes better than full? So, like when it's series parallel, it's optimal. Yeah. But do you know of any graph structures where it becomes better than full?
No, I don't think so. I mean, there's like, for the graph that we looked at, like if you have the breast graph, which then you cannot get better than 4/3, for example. Then this 4/3 is tight. But I don't know if there's... No, I mean, as soon as you're not series parallel anymore, then you can always have this breast graph in your graph as a subgraph, kind of. And then the 4/3 can be tight.
Did you think about private signals?
No. Well, we thought about this a little bit, but then, well, our idea was that this is not too realistic because you can just basically update again and get more and more private signals, and then just change your information by this.
Let me say we're still thinking about private.
Yeah.
I've been thinking about this for years.
Yeah.
You said K is small for realistic network. Is there a particular network that you tried this on?
Yeah, we tried this on Sioux Falls. Yeah. On Sioux Falls, this city in the States. Yeah.
So for the parallel link case, you proved that full information.
For which case?
So for the parallel link case,
Yeah.
you proved that full information is optimal, right? How would that result depends on that your setting is non-atomic routing. What if it's atomic routing?
What?
So
How does this?
How sensitive is that result to the assumption that you are doing non-atomic routing? There's one unit flow,
Yeah.
as opposed to an atomic routing case. There's an agent flow.
This I don't know. I haven't thought about this. Yeah.
But it relies on the assumption of linear latency.
Yeah.
Okay.
Yeah.
Okay, then let's thank Svenja again. Thanks.